0645 hours. RAF Kenley, 18 June 1940. Flight Lieutenant William Franklin checks his oxygen mask, adjusts his harness. The Supermarine Spitfire. Mark I sits heavy on the tarmac. 1,200 gallons of 100 octane, 8 Browning machine guns. 1 Rolls-Royce Merlin engine turning at idle. The propeller blades catch morning light. 2-position air screw. Fine pitch for takeoff. Coarse pitch for cruise. Nothing in between. Franklin knows the mathematics. Below 10,000 feet, the prop bites air efficiently. Above 20,000, it becomes a paddle churning through soup. The scramble bell cuts through dawn silence. Bandits inbound, vector 090, Angels 25. Franklin's thumb finds the starter. The Merlin coughs, catches. 12 cylinders firing in sequence, 2,600 RPM. The aircraft lurches forward, 620 meters of runway. Franklin holds the stick forward, keeps the tail down. Airspeed builds, 60 miles per hour, 70, 80. The Spitfire wants to fly, but the fixed-pitch propeller fights every revolution, like driving a car stuck in second gear. At 95 miles per hour, Franklin pulls back. The Spitfire claws into gray sky. 2,150 feet per minute, standard climb rate. Franklin watches the altimeter needle crawl clockwise. 5,000 feet, 8,000, 10,000. The propeller efficiency curve falls off a cliff. Each foot of altitude costs exponentially more power, 15,000 feet. The radio crackles. Hostile formation bearing 085, Heinkel 111s with escort. Franklin strains against his harness, scans the horizon. Nothing yet. His altimeter reads 18,000 feet, still climbing, still too slow. The mathematics are brutal. At this rate, he needs 4 more minutes to reach combat altitude. The Germans will be overhead in 3, 20,000 feet. Franklin levels off. His engine temperature runs hot. Manifold pressure drops. The 2-position propeller forces a compromise. Fine pitch would give him climb rate but costs top speed. Coarse pitch delivers speed but kills acceleration. He's stuck between 2 bad choices. There, black specks against cumulus. Heinkel 111s in formation. Messerschmitt 109s above them at 25,000 feet. Perfect combat spread. The Germans own the altitude advantage. Franklin banks left, tries to position for an intercept. The Spitfire responds but feels sluggish, like wrestling through molasses. He knows what comes next. The Messerschmitts will dive from above, use gravity and altitude for speed. He'll defend from below, react instead of attack. The first 109 peels off, starts its dive. Franklin pulls his stick back, climbs to meet the threat. The Merlin screams at maximum power, but the propeller can't translate that energy efficiently. Wrong pitch for the job. The German fighter closes distance. Franklin breaks right. The pull. Messerschmitt overshoots, climbs back to altitude, resets for another pass. Franklin knows he's losing this chess match 1 move at a time. His aircraft can't climb fast enough to contest the high ground, can't accelerate quickly enough to disengage. The 2-position propeller has him trapped in a tactical box. He survives the engagement. Barely. Lands with fuel gauges reading near empty and bullet holes in his port wing. On the ground, Franklin watches a team of engineers working on another Spitfire. They're installing something new, a different propeller, heavier, more complex, hydraulic lines running to the hub. The mechanics shake their heads. Too bloody complicated, one says. Give it a week. Thing'll fail when you need it most. The lead engineer looks up. Name tape reads Cook. He wipes oil from his hands. This unit maintains constant RPM, Cook says. Blade pitch changes automatically. Keeps the Merlin in its power band from sea level to 30,000 feet. Franklin examines the installation. The hub assembly looks like precision clockwork, hydraulic governor, pitch change mechanism, oil pressure lines. Nothing like the simple 2-position system he knows. What's the catch? Franklin asks. No catch, just physics. The test pilot fires up the modified Spitfire. Same Merlin engine, Same airframe, different mathematics. The takeoff run measures 560 meters instead of 620. The climb rate hits 2,900 feet per minute. Service ceiling jumps to 34,400 feet, 7,000 feet higher than before. Franklin does the calculation in his head. 7,000 feet means tactical advantage, means first shot opportunity, means survival. If you want to see how this too complex propeller performed against Luftwaffe pilots who were trained to kill Allied airmen, please hit that like button. It helps us share more forgotten stories like this. And please subscribe if you haven't already. Back to Cook's gamble that would change air warfare forever. The telephone rang at 0600 hours on 22nd June 1940. Lord Beaverbrook's voice cut through static from Whitehall. Secretary of State for Air. Direct orders to RAF maintenance commands across southern England. Convert all frontline Spitfires and Hurricanes to constant-speed propellers. Implementation begins immediately. Cook hung up the receiver at de Havilland Propellers. Grabbed his leather jacket. The factory floor stretched before him like an aircraft hangar. Rotoll constant-speed units lined the assembly benches. Each propeller hub weighed 500 pounds. 150 pounds heavier than the two-position units they would replace. The mechanics called them boat anchors. "Too heavy," said Chief Mechanic Roberts. "Aircraft will never get off the ground." Cook pulled the technical specifications from his briefcase, spread them across the workbench. The Rotoll unit used a hydraulic governor. System. Oil pressure controlled blade pitch. Engine RPM stayed constant at 2,800. Blade angle varied from 15 degrees fine pitch to 45 degrees coarse pitch. Automatic adjustment based on airspeed and manifold pressure. "Weight penalty is offset by performance gain," Cook said. "Service ceiling increases 7,000 feet. Climb rate improves 30%. Roberts shook his head. "More parts means more failures. Hydraulic lines, oil seals, pitch change mechanisms. Too complex for field maintenance." The first convoy of modified Spitfires arrived at RAF Biggin Hill on 24th June. Squadron leader Douglas led the acceptance trials. His aircraft carried the new Rotoll constant-speed air screw. 3-blade configuration. Each blade measured 11 feet 2 inches from hub to tip. Hydraulic oil lines ran from the engine compartment to the propeller hub. A governor unit mounted behind the firewall controlled oil pressure. Douglas ran through his pre-flight checklist: engine oil quantity, hydraulic reservoir level, pitch change mechanism operation. The constant speed unit added 17 separate inspection points to standard procedures. Ground crews grumbled about maintenance complexity. More systems meant more potential failures. "Engine start," Douglas called to his ground crew. The Merlin fired on the second attempt. 12 cylinders caught in sequence. Douglas advanced the throttle. The propeller governor held engine speed at 2,800 RPM. Blade pitch adjusted automatically. Fine pitch for ground operations. The aircraft rolled forward smoothly. Takeoff run measured 540 meters, 60 meters shorter than standard two-position configuration. Douglas pulled back on the stick at 92 miles per hour. The Spitfire lifted cleanly. No wallowing, no extended ground roll. The constant-speed propeller bit air efficiently from the moment of rotation. Climb performance exceeded specifications. Douglas reached 10,000 feet in 3 minutes 40 seconds. Previous best time was 4 minutes 50 seconds. The difference meant tactical advantage. RAF fighters could intercept German formations before they reached bombing altitude. Douglas pushed the Spitfire to 25,000 feet. Engine temperature stayed within normal limits. Manifold pressure held steady. The constant speed governor maintained optimal blade pitch throughout the climb. No manual adjustment required. The pilot could focus on navigation and threat assessment instead of propeller management. Service ceiling testing began on 26th June. Test pilot Henderson took a modified Hurricane to maximum altitude. Previous ceiling was 27,400 feet. The constant speed propeller pushed performance to 34,400 feet. 7,000 feet additional altitude. The mathematics were undeniable. "We can engage above the Germans now," Henderson reported over radio. instead of defending from below. Production ramped up across 3 facilities. De Havilland Propellers handled Spitfire conversions. Rotol Limited manufactured Hurricane units. Bristol Aeroplane Company provided backup capacity. Each installation required 4 days per aircraft. Skilled technicians removed the old 2-position air screw, installed the constant speed hub assembly, connected hydraulic lines, calibrated the governor mechanism, tested the pitch change operation. Supply chain problems emerged immediately. Hydraulic oil consumption increased 4-fold. Spare blade inventory ran low after 6 weeks. Hub bearings required specialized maintenance procedures. Ground crews needed additional training on governor adjustment and troubleshooting. The Air Ministry Procurement Office scrambled to meet demand. Field reports filtered back to Cook's engineering team. Pilots praised climb performance and altitude capability. Ground crews complained about maintenance complexity. Squadron commanders reported improved intercept success rates. Maintenance officers documented increased parts consumption and longer service times. Flying Officer Mitchell of 6-5 Squadron recorded combat performance data during July operations. His constant speed Spitfire reached 20,000 feet in 6 minutes 30 seconds. Previous time was 9 minutes 15 seconds. The improvement meant intercepting German formations before they reached target altitude. First engagement advantage instead of defensive reaction. "We're not chasing them anymore," Mitchell wrote in his pilot log. "We're waiting for them." Engine wear patterns shifted with constant speed operation. The Merlin ran at optimal RPM throughout the flight envelope, reduced stress on cylinder heads and pistons. Propeller hub failures remained rare. Hydraulic system reliability exceeded expectations. The mechanics' predictions of catastrophic complexity proved unfounded. By mid-August, conversion teams had modified over 1,000 aircraft. Every frontline Spitfire and Hurricane squadron operated constant speed propellers. The tactical balance shifted measurably. RAF fighters contested altitude advantage. German formations faced interception from above instead of below. Combat losses decreased among British pilots. Mission success rates improved across fighter command. Cook visited RAF stations to monitor field performance. He watched mechanics service the constant speed units, observed pilot briefings on governor operation, collected failure reports and maintenance logs. The data supported theoretical predictions. Complexity was manageable. Performance gains were substantial. The propeller innovation had transitioned from experiment to operational standard. The German response came in late August. Luftwaffe intelligence noted improved RAF fighter performance. British aircraft reached higher altitudes, climbed faster from takeoff, maintained better engine efficiency throughout combat operations. German pilots reported losing altitude advantage during engagements. The tactical equation had changed. The final Spitfire conversion completed at RAF Northolt on 16 August 1940. Squadron Leader Park signed the technical acceptance form. 1,047 aircraft now carried constant speed propellers. Every frontline fighter in fighter command. The 2-month retrofit campaign had ended. The real test began at dawn. Franklin adjusted his oxygen regulator at 25,000 feet. Below him, the English Channel stretched toward occupied France. Radar stations reported incoming formations. Large raid building over Calais. Heinkel 111s with Messerschmitt escort. Expected time on target, 0915 hours. The scramble order came at 0845. Franklin's Spitfire lifted from RAF Kenley in 400 meters. Shortened takeoff run meant faster intercept response. He climbed at 2,900 feet per minute. The constant speed propeller held his Merlin at optimal RPM. Blade pitch adjusted automatically as air density decreased with altitude. Bandits bearing 087, Angels 28, the controller reported. Franklin reached 28,000 feet in 8 minutes. Previous best time was 12 minutes. The altitude advantage belonged to RAF fighters now. Franklin could see the German formation climbing from French airspace. Heinkel bombers in tight formation, Messerschmitt fighters spread above them at 30,000 feet. Squadron formation assembled at altitude, 12 Spitfires holding position 2,000 feet above the incoming raid. Perfect intercept geometry. Franklin checked his gun switches. 8 Browning machine guns loaded with armor-piercing ammunition. 250 rounds per gun. Enough for 15 seconds of continuous fire. The German formation crossed the channel at 26,000 feet. Heinkel 111s loaded with high explosive bombs. Target London dock facilities. Fighter escort maintained combat spread above the bomber stream. Standard Luftwaffe tactics. Use altitude advantage to control engagement parameters. Franklin rolled his Spitfire into a diving attack. Airspeed built rapidly, 300 miles per hour, 350, 400. The constant speed propeller maintained thrust efficiency throughout the dive. No power loss from incorrect blade pitch, no engine overspeed from excessive RPM. He selected the lead Heinkel bomber, closed range to 300 yards, open fire. 8 guns converged on the target. Armor-piercing rounds punched through aluminum skin. The bomber's port engine caught fire. Smoke trailed from the wing root. Franklin broke left to avoid return fire. Pulled 4 Gs in the turn. His Spitfire responded cleanly. The constant speed propeller bit air efficiently throughout the maneuver. No loss of thrust during high G loading. The aircraft maintained energy better than previous configurations. The damaged Heinkel fell out of formation. Crew bailed out over the channel. Franklin counted 3 parachutes. The bomber crashed into gray water 12 miles southeast of Dover. First confirmed kill using constant speed propeller technology. Combat continued at altitude. RAF fighters attacked from above. Messerschmitt escorts dove to engage. Franklin found himself in a turning fight with a 109 at 24,000 feet. Both aircraft pulled maximum Gs engines at combat power. The German fighter used standard tactics. Dive to build speed. Climb to extend range. Reset for another attack. Franklin countered with sustained turning combat. His constant speed propeller maintained thrust throughout the engagement. The Messerschmitt's fixed-pitch air screw lost efficiency during high-angle maneuvering. Franklin gained angles advantage after 6 turns. Closed to 200 yards. Fired a 3-second burst. Rounds struck the Messerschmitt's cockpit and engine compartment. The German aircraft rolled inverted and dove toward the channel. No parachute observed. Post-mission debriefing revealed tactical changes. RAF fighters engaged at higher altitudes than previous operations. Climb performance allowed intercept before German formations reached bombing altitude. Combat losses decreased by 40% compared to July statistics. Intelligence reports from captured German aircrews confirmed the shift. Luftwaffe pilots noted improved RAF fighter performance. British aircraft climbed faster, maintained better altitude, sustained combat power longer during engagements. The tactical balance had reversed. Cook visited maintenance facilities to assess field performance. Ground crews reported increased complexity but manageable procedures. Hydraulic system reliability exceeded specifications. Hub failures remained minimal. The mechanics had adapted to constant speed maintenance requirements. Still heavier than the old props, Chief Roberts admitted, but the performance gain is undeniable. Spare parts consumption stabilized by late August. Initial supply shortages resolved through expanded production. Hydraulic oil requirements leveled at predictable rates. Blade replacement schedules established based on operational data. The logistics pipeline supported continued operations. German response became evident in early September. Luftwaffe units began receiving VDM constant speed propellers for Messerschmitt 109s. The technology gap was closing. British advantage would be temporary without continued innovation. Franklin's combat log recorded 12 enemy aircraft destroyed by mid-September. All engagements occurred above 25,000 feet. The altitude capability of his constant speed Spitfire enabled intercepts impossible with previous configurations. Tactical advantage translated directly into combat success. Engine manufacturers noted reduced wear patterns on Merlin engines equipped with constant speed propellers. Optimal RPM operation. Throughout flight regimes decreased cylinder stress. Piston ring wear diminished. Valve timing remained stable longer between overhauls. The propeller innovation improved overall power plant reliability. Production statistics showed increasing adoption across Allied air forces. United States Army Air Corps ordered constant-speed units for P-40 fighters. Royal Australian Air Force requested conversions for Pacific theater operations. The technology spread beyond fighter command to global applications. Cook reviewed performance data in his engineering office. Climb rate improvements averaged 28% across all aircraft types. Service ceiling gains measured between 6,000 and 8,000 feet. Takeoff distance reductions ranged from 8 to 12%. The specifications had been validated through combat operations. Tactical doctrine evolved to exploit constant speed capabilities. Fighter squadrons developed high-altitude intercept procedures. Controllers positioned aircraft above incoming raids instead of below. Pilots trained for sustained combat at extreme altitudes. The technology enabled new operational concepts. By October, German formations approached at higher altitudes to counter RAF advantages. Heinkel bombers climbed to 32,000 feet. Messerschmitt escorts operated above 35,000 feet. The altitude war escalated as both sides adapted to new performance parameters. Franklin reached 34,000 feet during an intercept on 5 October. His Spitfire maintained full combat capability at maximum service ceiling. The constant speed propeller delivered thrust efficiency throughout the climb. No performance degradation at extreme altitude. The engagement occurred 2 miles above the English Channel. RAF fighters attacked a formation of Dornier bombers at 33,000 feet. Franklin scored hits on the lead aircraft. The bomber broke formation and descended rapidly. Combat effectiveness remained high despite extreme operating conditions. The first VDM constant-speed propeller arrived at Luftwaffe testing facilities on 3 September 1940. German engineers stripped the unit from a captured Messerschmitt 109, hydraulic governor mechanism, variable blade pitch control, oil pressure regulation system. The technology matched British Rotol specifications almost exactly. Oberst-Müller examined the propeller hub at Rechlin Test Center. VDM construction used different materials but identical operating principles. German metallurgy favored steel components over British aluminum. Heavier construction but increased durability. The performance characteristics remained equivalent. How many aircraft can be converted? Müller asked his technical staff. Initial production allows 50 units per month, replied Hauptmann Weber. Full-scale manufacturing reaches 200 units by January 1941. German test pilots evaluated the VDM system on modified Messerschmitt fighters. Climb rate improved 25%. Service ceiling increased 6,000 feet. The performance gains matched RAF advantages. Parity was achievable through technology adoption. Franklin intercepted a German formation over Kent on 7 September. The engagement occurred at 28,000 feet, standard altitude for recent operations. Franklin climbed to intercept position in 7 minutes. His constant-speed Spitfire maintained tactical advantage through superior performance. The lead Messerschmitt dove to attack. Franklin recognized different flight characteristics. The German fighter climbed steeper than previous encounters, maintained thrust efficiency throughout the maneuver. The enemy had closed the technology gap. Combat ensued at high altitude. Both aircraft used constant-speed propellers. Performance parity eliminated previous British advantages. The engagement became a pilot skill contest instead of equipment superiority. Franklin traded altitude for position, maneuvered for gun solution. He fired a 4-second burst at 200 yards range. Armor-piercing rounds struck the Messerschmitt's wing root. The German fighter rolled away trailing smoke. Franklin pursued through a diving spiral. Both aircraft exceeded 400 miles per hour in the descent. The damaged Messerschmitt crashed near Canterbury. Franklin claimed his 15th confirmed victory. Post-flight examination revealed advanced German propeller technology. The tactical balance was shifting toward equipment parity. Intelligence reports confirmed widespread Luftwaffe adoption of constant-speed propellers. Production facilities at VDM and Junkers manufactured units for frontline squadrons. German fighters operating over Britain showed improved climb and altitude performance. The British advantage was diminishing rapidly. Cook received technical specifications for captured German propellers. VDM construction used precision manufacturing techniques. Tolerances matched or exceeded British standards. German engineering had reverse-engineered constant speed technology successfully. "They're producing better units than our initial models," Cook told his engineering staff. Heavier, but more reliable construction. Supply chain problems emerged across RAF maintenance facilities. Constant speed propeller consumption exceeded production capacity. Hydraulic failures increased with operational tempo. Blade replacement requirements strained inventory levels. The complex systems demanded more resources than anticipated. Roberts supervised emergency repairs at RAF Biggin Hill. 3 Spitfires grounded with hydraulic leaks. 2 more aircraft awaiting blade replacements. Squadron strength reduced by 20% due to maintenance issues. "Simple systems don't fail like this," Roberts complained to visiting officials. 2 position props needed basic maintenance. These units require specialized knowledge. Franklin's aircraft developed governor problems. During a patrol on 12 September, blade pitch oscillated between fine and coarse settings. Engine RPM varied uncontrollably. He aborted the mission and returned to base on manual propeller control. Ground crew investigation revealed contaminated hydraulic oil. Metal particles from governor wear had clogged the pitch change mechanism. Repair required complete propeller removal and overhaul. The aircraft remained grounded for 6 days. German tactical adaptations appeared by mid-September. Luftwaffe formations approached at extreme altitudes to negate RAF intercept advantages. Heinkel bombers operated above 35,000 feet. Fighter escorts climbed to 40,000 feet. The altitude war escalated beyond previous parameters. Franklin's squadron received orders to intercept high-altitude raids. Service ceiling limitations became critical factors. His constant-speed Spitfire reached 34,000 feet maximum. German formations operated beyond effective intercept range. The engagement on 15 September occurred at the limit of British performance. Franklin climbed to maximum altitude but arrived below the German formation. Messerschmitt fighters dove from above. Altitude advantage returned to Luftwaffe tactics. Franklin defended against diving attacks but could not pursue climbing German aircraft. His Spitfire lost thrust efficiency above 32,000 feet. The constant speed propeller maintained optimal blade pitch, but engine power decreased with air density. Combat effectiveness declined at extreme altitudes. Gun accuracy suffered in thin air. Aircraft handling became sluggish above 30,000 feet. Pilots experienced fatigue from oxygen system limitations. High-altitude operations pushed equipment and personnel beyond optimal parameters. Production statistics revealed the cost of complexity. Constant-speed propeller manufacturing required 40% more materials than 2-position units. Assembly time increased by 60%. Quality control procedures tripled inspection requirements. The advanced technology demanded substantial resources. Engine wear patterns shifted with extended high-altitude operations. Merlin power plants operated at maximum settings for longer periods. Cylinder head temperatures increased. Oil consumption rose. Maintenance intervals shortened between overhauls. The performance gains carried operational costs. Franklin's combat log recorded decreasing success rates through September. German aircraft performance matched British capabilities. Tactical advantages from superior equipment disappeared. Combat became a contest of pilot skill and squadron tactics rather than technological superiority. Cook analyzed failure reports from operational squadrons. Hydraulic system reliability remained acceptable, but required increased maintenance attention. Blade fatigue occurred earlier than projected. Governor mechanisms needed calibration more frequently than anticipated. The field data revealed implementation challenges. Training programs expanded to address maintenance complexity. Ground crews received additional instruction on hydraulic systems. Propeller specialists deployed to frontline squadrons. Technical manuals were revised based on operational experience. The support infrastructure adapted to advanced technology requirements. German intelligence gathered through prisoner interrogations confirmed British performance advantages from constant-speed propellers. Luftwaffe technical staff accelerated VDM production schedules. Additional manufacturing facilities received priority resource allocation. The technology race intensified on both sides. Franklin scored his final victory of the Battle of Britain on 26 September. The engagement occurred at 31,000 feet over the Thames estuary. His target was a Dornier bomber separated from formation. Single aircraft engagement under ideal conditions. He approached from the bomber's blind spot, closed range to 150 yards, fired a sustained burst into the aircraft's port engine. The Dornier caught fire immediately. Crew bailed out over water. Franklin observed 4 parachutes before the aircraft crashed. The victory demonstrated constant speed propeller effectiveness under optimal circumstances, high-altitude interception, perfect approach geometry. Concentrated firepower on vulnerable target. The technology enabled tactical success when properly employed. German formations adapted by maintaining tighter defensive formations. Fighter escorts provided closer protection for bomber streams. Altitude separation between bombers and fighters decreased. Tactical flexibility countered technological advantages through improved procedures. The United States Army Air Corps placed orders for 3,000 constant-speed propellers in November 1941. Hamilton Standard received the contract. American production lines retooled for hydraulic governor systems. The technology that began as an experimental RAF modification became standard equipment across Allied air forces. Cook watched American engineers tour his facility at de Havilland Propellers. They measured hub assemblies, photographed hydraulic connections, recorded governor specifications. The British innovation was being scaled for mass production across the Atlantic. "How many aircraft per month?" asked Colonel Patterson from Wright Field. "Current capacity allows 200 units monthly," Cook replied. Expanded production reaches 800 by mid-1942. Franklin flew his 100th operational sortie on 3 December 1941. His Spitfire carried the same constant-speed propeller installed 18 months earlier. Hub bearings showed minimal wear. Blade pitch mechanisms operated within specifications. The technology had proven reliable through extended combat operations. Engine maintenance reports revealed unexpected benefits from constant speed operation. Merlin power plants equipped with hydraulic propellers showed reduced cylinder wear. Optimal RPM operation throughout flight regimes decreased mechanical stress. Average time between overhauls increased by 30% compared to fixed-pitch configurations. Roberts supervised the first major overhaul of constant-speed propellers at RAF Kenley. Hydraulic seals required replacement after 800 flight hours. Governor mechanisms needed recalibration every 400 hours. Blade inspections occurred at 200-hour intervals. The maintenance schedule was complex but manageable. "Still more work than two-position props," Roberts admitted, "but the reliability exceeds expectations." German production statistics showed rapid expansion of VDM constant-speed manufacturing. Messerschmitt 109 production included hydraulic propellers as standard equipment by January 1942. Focke-Wulf 190. Fighters received constant-speed units from initial delivery. The technology gap had closed completely. Franklin engaged German formations over occupied France in March 1942. Both sides operated aircraft with equivalent propeller technology. Performance parity eliminated previous tactical advantages. Combat success depended on pilot skill and numerical superiority rather than equipment differences. The engagement occurred at 32,000 feet. Franklin led a squadron of 12 Spitfires against 15 Messerschmitt 109s. Both formations climbed to intercept altitude in similar time frames. Constant speed propellers provided equal performance capabilities. Franklin selected a target and maneuvered for attack position. The German pilot countered with climbing turns. Both aircraft maintained thrust efficiency throughout high-angle maneuvering. Neither gained decisive advantage through propeller performance. The dogfight became a test of flying skills. Combat lasted 12 minutes before German fighters disengaged. Franklin's squadron claimed 3 enemy aircraft destroyed. RAF losses totaled 2 Spitfires. The exchange rate reflected equipment parity rather than technological superiority. Supply chain analysis revealed the cost of complexity across Allied air forces. Constant speed propellers required specialized manufacturing techniques. Hydraulic components demanded precision machining. Quality control procedures increased production time by 40% compared to fixed-pitch units. Material consumption statistics showed resource implications. Each constant-speed propeller used 60 pounds more aluminum than two position equivalents. Hydraulic fluid requirements increased maintenance supply needs. Specialized tools and training added logistical burdens to frontline operations. Cook developed pneumonia in April 1942. He spent 3 weeks in hospital while his engineering team continued propeller production. The technology he championed had become routine across RAF Fighter Command. Innovation transformed into standard operating procedure. Recovery brought new challenges. United States Navy requested constant-speed propellers for carrier-based fighters. Pacific theater operations demanded equipment capable of extreme environmental conditions. Salt air corrosion threatened hydraulic systems. Temperature variations affected governor calibration. Franklin received promotion to squadron leader on 15 May 1942. His combat experience totaled 130 sorties with 19 confirmed victories. 16 kills occurred while flying aircraft equipped with constant-speed propellers. The technology enabled tactical success through superior performance. American production exceeded British output by July 1942. Hamilton Standard manufactured 1,000 constant-speed units monthly. Curtiss Wright produced an additional 600 units. United States industrial capacity scaled propeller technology beyond RAF requirements. Tactical doctrine evolved to exploit mass production capabilities. Heavy bomber formations required fighter escorts with extended range and altitude performance. Constant-speed propellers enabled escort missions previously impossible with fixed-pitch equipment. Strategic bombing campaigns depended on advanced propeller technology. Franklin flew his final combat mission on 12 December 1940. His aircraft suffered engine failure during patrol over the English Channel. Hydraulic pressure loss caused propeller blade pitch to freeze in course position. Engine RPM dropped below sustainable power settings. He attempted emergency landing at RAF Manston. Approach speed remained too high due to fixed course pitch. The Spitfire touched down at 120 miles per hour. Landing gear collapsed on impact. Franklin survived but sustained serious leg injuries. Medical examination revealed combat fatigue from extended operations. 18 months of high-altitude flying had affected his oxygen tolerance. Repeated G-force exposure caused circulatory problems. Physical stress from advanced combat aircraft exceeded human endurance limits. Roberts conducted failure analysis on Franklin's propeller system. Hydraulic line rupture occurred near the governor mechanism. Metal fatigue from vibration caused seal failure. Oil pressure loss prevented pitch change operation. The incident highlighted reliability concerns with complex systems. Replacement pilots arrived at RAF squadrons with extensive training on constant-speed propeller operation. Flight schools included hydraulic system procedures in standard curricula. Maintenance training programs expanded to cover advanced propeller technology. The learning curve had been institutionalized. Production statistics for 1942 showed complete transition to constant-speed propellers across Allied fighter aircraft. British factories delivered 4,000 units. American manufacturers produced 12,000 units. The technology that began as experimental equipment became universal standard. Cook returned to limited duty in January 1943. His engineering responsibilities shifted from development to quality control. The innovation phase was complete. Manufacturing reliability became the primary focus. Mass production demanded consistent performance across thousands of units. German production reached parity by spring 1943. Luftwaffe fighters operated constant-speed propellers as standard equipment. Performance advantages disappeared through technological diffusion. Combat effectiveness depended on pilot training and tactical doctrine rather than equipment superiority. Franklin observed new pilot training from his hospital bed. Young aviators learned constant speed operation as basic flight procedure. The complex hydraulic systems that once seemed revolutionary were now routine technology. Innovation had become standard operating knowledge. The war continued with constant speed propellers as baseline equipment. No side maintained technological advantage through propeller design. Future innovations focused on engine power and aircraft aerodynamics. The gear shift of the air had transformed from breakthrough technology to mundane necessity. Cook reflected on the transformation while reviewing production reports. His engineering team had solved a complex technical problem under wartime pressure. The solution became standard across global air forces. Innovation succeeded through practical application rather than theoretical perfection. The war ended on 8th of May 1945. Victory celebrations filled London streets, while maintenance crews at RAF stations continued servicing constant-speed propellers. The technology that once seemed revolutionary had become routine maintenance procedure. Ground crews replaced hydraulic seals without considering the innovation they represented. Franklin walked with a permanent limp through the de Havilland factory in June 1945. His leg injuries from the December crash had healed imperfectly. Combat flying was impossible, but his technical knowledge remained valuable. The Air Ministry assigned him to propeller development programs. "Still too complex," Roberts muttered, while supervising peacetime conversions. Fighter squadrons were being scaled down. Hundreds of constant-speed propellers sat in storage hangars. The wartime production surge had created massive surplus inventory. Cook reviewed production statistics in his office. Allied forces had manufactured over 200,000 constant-speed propellers during the war years. British factories produced 60,000 units. American manufacturers delivered 140,000. The scale represented industrial transformation from experimental technology to mass production. Cost analysis revealed the true expense of complexity. Each constant-speed propeller required 4 times the manufacturing hours of fixed-pitch equivalents. Material consumption was 60% higher per unit. Quality control procedures tripled inspection requirements. The performance advantage had demanded substantial resources. Commercial aviation adopted constant-speed propellers for passenger aircraft in late 1945. Airlines required efficient operation across varying flight conditions. The technology that proved itself in combat found civilian applications. Douglas DC-6 aircraft received Hamilton Standard constant speed units as standard equipment. Franklin examined civilian propeller specifications. Commercial requirements differed from military applications. Reliability took precedence over maximum performance. Maintenance intervals extended to 1,000 hours between inspections. The technology adapted to peacetime operational requirements. Training programs at civilian flight schools included constant-speed propeller instruction. Student pilots learned governor operation as basic procedure. The complex hydraulic systems that once challenged experienced mechanics became standard curriculum for commercial aviation students. Cook received an engineering award from the Royal Aeronautical Society in September 1945. The citation recognized his contribution to Allied victory through propeller innovation. He accepted the honor but noted that success required extensive team effort across multiple organizations. Individual innovation means nothing without production capability, Cook said during his acceptance speech. We succeeded because British industry scaled experimental technology into operational reality. Post-war analysis quantified the tactical impact of constant-speed propellers. RAF Fighter Command statistics showed 30% improvement in intercept success rates after conversion. Climb performance gains averaged 28% across all aircraft types. Service ceiling increases ranged from 6,000 to 8,000 feet. German records captured after surrender confirmed the technology's strategic importance. Luftwaffe intelligence reports from 1940 noted sudden improvements in RAF fighter performance. The constant-speed propeller adoption had shifted tactical balance during critical phases of the Battle of Britain. Franklin studied captured German propeller designs in his new role as technical liaison. VDM construction quality matched or exceeded British standards. German engineering had successfully reverse-engineered and improved upon Allied innovations. The technology race had driven improvements on both sides. Manufacturing efficiency became the primary focus during peacetime conversion. Wartime production methods emphasized speed over cost control. Peacetime operations required profitable manufacturing techniques. Engineering teams redesigned production processes to reduce complexity and expense. Cook's health declined through late 1945. Extended wartime stress had affected his cardiovascular system. Long hours and constant pressure during the development phase had taken physical toll. His doctor recommended reduced responsibilities and shorter working hours. Roberts assumed increased maintenance supervision as experienced personnel left military service. Peacetime RAF required skeleton crews to maintain reduced aircraft inventories. Knowledge preservation became critical as wartime experts returned to civilian occupations. Training documentation captured lessons learned during operational deployment. Technical manuals included field modifications developed by maintenance crews. Troubleshooting procedures reflected actual failure modes encountered during combat operations. The accumulated knowledge became institutional memory. Franklin married his nurse from the military hospital in November 1945. The wedding ceremony took place at a small church near RAF Biggin Hill. His squadron mates who survived the war attended the service. Combat veterans shared memories of constant speed propeller operations during the Battle of Britain. Commercial aviation growth drove continued propeller development. Airline operations demanded improved reliability and reduced maintenance requirements. Engineering teams focused on durability rather than maximum performance. The technology matured from wartime innovation to civilian transportation standard. Cook retired from active engineering duties in March 1946. His replacement was a younger engineer with extensive wartime production experience. The transition represented generational change from innovation pioneers to manufacturing specialists. Statistical analysis of wartime propeller failures revealed reliability patterns. Hydraulic system problems accounted for 30% of maintenance issues. Blade fatigue caused 20% of failures. Governor mechanism problems represented 15% of service interruptions. The data guided post-war design improvements. Franklin accepted a position with British Overseas Airways Corporation in April 1946. His combat experience and technical knowledge qualified him for flight operations management. Commercial aviation offered opportunity to apply wartime lessons to civilian transportation. Manufacturing facilities converted from military to commercial production. Hamilton Standard retooled assembly lines for airline propeller requirements. De Havilland propellers focused on general aviation markets. Wartime capacity found peacetime applications across multiple aviation sectors. Cook moved to a cottage in the Cotswolds in summer 1946. Rural retirement provided respite from wartime stress and industrial pressure. His garden included a workshop where he continued experimental propeller designs as personal projects rather than military requirements. The technology he championed had transformed aviation permanently. Every major aircraft manufacturer adopted constant speed propellers as standard equipment. The innovation spread globally through commercial aviation growth and military technology transfer programs. Franklin's first commercial flight as operations manager occurred on 15 August 1946. The BOAC flight from London to New York used Lockheed Constellation aircraft equipped with Hamilton Standard constant speed propellers. Passenger service benefited directly from wartime technological developments. Training programs at civilian aviation schools standardized constant speed propeller instruction. Student pilots learned governor operation alongside basic flight procedures. The technology that once required specialized knowledge became routine training curriculum for commercial aviation personnel. Roberts supervised disposal of surplus military propellers at storage facilities across Britain. Thousands of units manufactured for wartime production exceeded peacetime requirements. Scrap metal recovery provided materials for civilian manufacturing while reducing government inventory costs. The constant speed propeller had fulfilled its wartime purpose. Allied victory owed partial debt to technological advantages gained through superior propeller performance. The innovation provided tactical edge during critical periods when equipment superiority influenced combat outcomes. Cook reflected on the transformation while tending his garden. Complex hydraulic systems that once challenged the finest engineers were now maintained by civilian mechanics. Innovation had become commonplace through successful implementation and widespread adoption. The gear shift of the air had evolved from experimental concept to universal standard. Future aviation development would build upon the foundation established during wartime pressure. The technology lived on through continued improvement and application across global aviation markets.